The experiment we are currently performing, we call it the sickening drive. We're testing in a rather extreme driving scenario where we're slaloming. We're testing how much time it takes to get sick. What we're also testing is what happens within your body, what happens to your postural sway, what happens to your heart rate, what happens to your skin response, because that may provide us insight in the process, but may also help us to detect the beginning of motion sickness.
Delft University has great knowledge about the biomedical aspects of the human body. We want to modelize this knowledge and integrate it in the vehicle system, in the vehicle control in general. All this will help us to better adapt our active suspension in order to answer the needs of the passenger in each vehicle.
The engineer needs to have a mathematical solution to develop the control algorithms for the automated vehicle. And that means that we need a translation from the vehicle motion to the motion sickness development. To achieve that, we need biomechanical models of how the vehicle motion is transmitted from the seat to the body to the head. Because it is the head where we perceive motion with our vestibular organ and with our visual senses. And what we develop on top of that is a model of the sensory integration of vestibular and visual feedback, which then gives as additional output a prediction of the motion sickness development in time. In the end, that is a mathematical tool which translates vehicle motion to motion sickness.
Together with Delft University, we are working very hard to understand the fundamentals of motion sickness so that we'll be able to develop control algorithms that will be integrated in our active suspensions to better manage the motion of the vehicle.
Monroe is always at the cutting edge of technology for suspensions. And right now they have big engineering centers all around the world and they all work together.